Welcome to Topology Lesson 3 on surfaces. We're going to talk about Euler's characteristic. That's actually the equation we mentioned. We didn't give you the actual constants, but the equation we mentioned at the end of the last lecture, which I'll give you the answer on the next slide. At the end of the last lesson, I left you with this problem of finding the relationship between V, E, and F for these 6 polyhedra, and I noted that the equation will hold in general for polyhedra, convex polyhedra, and hopefully you got the answer, but if you didn't, here it is. It's V minus E plus F equals 2. We can just check a few of these. Let's try the octahedron. So we have 6 minus 12, that's a minus 6, and you add 8, you get plus 2. Let's try the icosahedron. 12 minus 30 is minus 18, you add 20 and you get 2 again. Let's just do the last one here. We get 10 minus 15 is minus 5, plus 7 is 2. So it holds for all these, and as I say, it holds in general. Excuse me. We'll actually prove that kind of a sketch in the next slide. In terms of history, the Euler characteristic was originally defined for polyhedra and used to prove various theorems about them, including the classification of the Platonic solids. It was stated for Platonic solids in 1537 in an unpublished manuscript by Francesco Moralico. The famous mathematician Leonhard Euler, for whom the characteristic is named, introduced it for convex polyhedra, more generally, but failed to rigorously prove that as an invariant. So that's sort of a very brief history. And as I mentioned, even though these shapes were known, going back BC, the pattern wasn't discovered until much later, which is kind of amazing, because once it's kind of put in front of you the way I did here, I'm sure any of these famous mathematicians from the past would have noticed it, but I guess they just never thought of actually looking for a pattern, and that was the key. Euler's characteristic also works for connected planar graphs, and you get the same value when you take the vertices minus number of edges plus the number of faces. There's one nuance, one catch, is that we need to include as a face the exterior of the planar graph. So let's look at a few here. We have this shape here, which obviously is connected. The number of vertices are 1, 2, 3, 4, 5, 6, 7. 7 vertices. The edges are a little bit trickier. We have 1, 2, 3, 4, 5, 6. Then another 4 from these lines in here. So that's 10. And then we get 4 faces inside and 1 exterior. We get 7 minus 10 plus 5 equals 2. Okay, we have a few more examples. I'll leave this one for you to verify that it actually equals 2, but let's do this one. Number of vertices is 1 in the middle, and then 1, 2, 3, 4, 5, so that's 6 altogether. Number of edges, 5 on the exterior and 5 inside, so that's 10. Number of faces, 1, 2, 3, 4, 5, and then again we had to count the exterior. That gives us 6, so we get 6 minus 10 plus 6, and that's 12 minus 10. That gives us 2. And then we can even have a connected graph like this, which is a tree. You notice there's no interior in this case, there's just an exterior. So number of vertices are 1, and we have to count the endpoints here too. So it's 1, 2, 3, 4, 5, 6, 7. So 7 vertices. The number of edges, 1, 2, 3, 4, 5, 6. 6 edges, and then there's just the one face, so to speak. It's the, I don't know, you can call it the, I guess it's the exterior to the shape. So we get 7 minus 6 plus 1, and again we get 2. So quite amazing, and you can play around with it. I would invite you to make up your own connected planar graph, and at least do one, and just verify that the formula works. So the two catches, I guess. One is you need to count the exterior. Then if you have something like this that's not closed, you need to remember to count the leaves, the whatever you want to call these things here, the end points that have only one one edge to connected to it. So let's prove our theorem for connected planar graphs. We have the number of vertices, edges, and faces of a connected planar graph. Follow this formula here, which we gave a few examples of in the previous slide. So we're going to use induction on the number of faces. We'll first prove the result if you have one face, and then we'll assume the result is true for k faces and show that it must follow that it's true for k plus 1 faces. So let's do the case for one face. In that case, G cannot have any cycles, otherwise the interior and the exterior of the cycle would give rise to at least 2 distinct faces. So in that case, G has no cycles, and by definition it's a tree. Then from a theorem in graph theory, we must have the number of vertices in a tree is one more than the number of edges. So I gave a reference here. You can look that up in my book, which I mentioned is freely available in the introductory video. I give the actual reference to my book. So we have the number of vertices equals the number of edges plus 1 in the case of a tree. And so we have just taking V minus E plus F, then plugging in this here, we get E plus 1 minus E, and then the number of faces is 1, and we see that when we compute this we get 2. So we've proven the result for F, number of faces equals 1, F equals 1. We assume it's true for F equals K, and let G be a connected planar graph with K plus 1 greater than or equal to 2 faces. Since trees have only one face, G cannot be a tree, and thus it must have a cycle. That's a basic result from graph theory. Then we choose any edge in the cycle and remove it from G, forming a new graph, which we call H. So that's G minus the one edge we remove. So we draw a figure. So let's say that's our we can draw it here. So we have the example here of a graph, and what we're saying is to remove one of the edges. So for example, it's not working. Let's make it yellow. So this thing in yellow, let's say we remove that. We remove this, and then what's left is this graph H, which equals G minus this edge here. So we've basically opened up this one cycle. So clearly the number of edges for the H is the number of edges in G minus 1. So that's all we've done is remove one edge. We've left the two vertices in place. and the number of vertices is the same. So again, we just removed the edge but not the two endpoints. All right, so let's continue on the next slide. So we talked about the number of edges and the number of vertices, but the number of faces for H would be the number of faces in G minus 1, since the edge E that we remove, being part of a cycle, must separate two faces of G, which are now joined in the one face that we remove the edge. So in our little example there, when we remove that one edge, we basically combine that enclosed face with the exterior face. But again, there's other possibilities. By a basic result from graph theory, I give a reference here, H is still connected, and so our induction hypothesis applies to H. Thus, we have here that, just looking on the left, the number of vertices minus the number of edges plus the number of faces for H equals 2. And then we can plug in the various results we had. So remember, we said the number of vertices of H is the same as the number in G. The number of edges of H was less than the number of edges in G. And the number of faces in H was 1 less than the number of faces in G. And then if we take these together, we get a minus 1 here. So it's a plus 1 minus 1. And we just get this sum here, which is the Euler equation for G. And then if we check the equalities, go all the way to the left, we see that the Euler's characteristic holds for G, which is what we wanted to prove. So that completes our theorem, or the proof of our theorem, I should say. In general, the Euler characteristic holds for a convex polyhedron, not just the connected planar graphs that we showed in the previous theorem. So I have a theorem here for any convex polyhedron, and more generally to any polyhedron whose boundary is topologically equivalent to a sphere and whose faces are topologically equivalent to this. The relationship between the number of vertices, edges, and faces is given by the Euler characteristic V minus E plus F equals 2. So we'll just give a sketch. The actual proof is not easy. It takes quite a bit. I gave a reference here, Epstein's book. But just in general, to give you an idea, you take a given polyhedron and remove one of its faces. So think of maybe a cube, and just take the top off and then flatten the remaining figure into a planar graph. The assumption that the polyhedral surface is homeomorphic to the sphere is what makes this possible. Remember, I stated that's part of the theorem. The flattened figure has one less face than the original, but recall for planar graphs we count the exterior region as a face, which brings us back to the same number of faces as the original polyhedron, and thus we can apply the theorem that we just proved. So an obvious question here is, how far does this theorem we go? We kind of started out with the Platonic solids and one additional example, the prism, and then we showed that the Euler characteristic worked for planar graphs, and then we, in the last slide, kind of give a sketch of a proof for convex polyhedra. What about something that has a hole in it, like this shape here, which is called a toroidal polyhedron? So if it's a little bit hard to count here, but if you do the counting, it has 24 vertices, 48 edges, and 24 faces. And when you do the formula here, you come up with 0. So we don't get the 2 that we had gotten before, and that actually has to do with the hole. So there's different values for the result of taking the vertices minus the number of edges plus the number of faces, depending on the shape of the figure, and in particular the number of holes that it has. I have another example for you on the next slide. The figure shown here is called a hexagonal torus, and if we took the number of vertices minus the number of edges plus the number of faces, I realize it's a bit hard to count, but take my word for it, if you do that for this, you'll get 0 again, similar to what we had in the previous slide. So this is basically an approximation of a torus. If we kept making even more segments here and we could get closer and closer. And in fact, the torus itself, even though it's smooth, and we'll see this in a minute, it has an Euler characteristic of 0. So even smooth shapes have an Euler characteristic. They could equal 2, they could equal 1, they could equal 0. There's different possible values, and we'll see. That's kind of related to this whole classification that we want to get at. So the value of the Euler characteristic depends on certain general characteristics of the shape. What we have here is another way of determining the Euler characteristic of a torus. On the previous slide, we had sort of a complex argument where we claimed that the limit of making more and more segments would eventually come to be a torus, and each one of those approximations had an Euler characteristic of 0. This approach here, we start with a rectangle, and we know that from our previous theorem about connected planar graphs, that it has a Euler characteristic of 2. And if we just take these two edges here and fold it to get a cylinder, then this vertice and this vertice can now coincide. It's up at the top, and this vertice now coincide. So there's only 2 vertices, and the number of edges is 3. There's this edge around the top, there's this edge here, which used to be 2 edges, and then there's the edge around the bottom, so that's 3. And then the number of faces is just 1. That's the what we call it, the surface itself of the cylinder. So we get 0 here, and then if we think of this being stretched and then joining the top to the bottom, we get this shape here. We get a torus, and recall we can bend and stretch things in topology, and they're equivalent. And so this is equivalent to this, is equivalent to this. And then if we look at this here, and we do the Euler characteristic, we get the number of vertices is 1, because now this vertex and this vertex are joined. So we just get 1 vertex. There's 2 edges, this one here, and then this one going around long ways, and then there's just 1 face. So no matter where you pick any point here, you can get to any other point without crossing any of the edges. So we get 0. And so this kind of is a high-level proof that the torus has Euler characteristic 0. And of course, you can bend this in many different ways. The main point here is it has a hole in it. So the shapes shown here on this slide are called fundamental polygons, and we already looked at 2 of them. One was the cylinder, and recall from the last slide I actually joined the vertical edges, but I've drawn it here as the horizontal edges being joined. So if you join these 2 edges, you get a cylinder. And we talked through the fact that the characteristic equation equals 0 in that case, and then we joined the the two, basically the top and bottom of the cylinder, to get a torus, and we reasoned that that had a characteristic of 0. There's other possibilities. You can get a Möbius strip by first twisting. You notice the arrows are going in different directions here. So if you take this strip, twist it halfway, and then join the edges, you get a Möbius strip. I'll show you that in more detail on the next slide. And that has a characteristic of 0. Then the next two are more complex. I'll talk about those on separate slides following this one, but we've just introduced it here. So for the Klein bottle, we first create the cylinder, and then rather than just joining the top and bottom of the cylinder, we twist it. You see here the arrows are going the opposite direction. So how you can basically make that happen is you need to go into 4 dimensions to do that. So it's not easy to visualize, but we'll talk about that. And that has a characteristic of 0, another characteristic of 0. And then the projective plane is even more complex. You first twist it and create a Möbius strip, and then you twist it again. These two edges you twist yet again, and then join those. And if you can visualize that, you're pretty good. So I'll try to talk through this, but it's not obvious. But you do get a characteristic of 1. Here's a picture of a Möbius strip. You can make one pretty easily. Just get a long strip of paper, twist it halfway, and then join it at the short edge, and you get this shape here. And if you build it using our fundamental polygon technique, then what you have here is we can count you get one edge here where you've joined, and then there's another edge here that we stop when we hit this other edge, and then there's another edge here. Again, we stop when we hit the edge B. So you get 3 edges. Number of vertices is 2. This one here, this B2 is connected to B4, and B1 is connected to B3. So there's 2 vertices. And then there's 1 face. So we have this formula here, 2 minus 3 plus 1, and we get 0. And if you like, there's another way of viewing this. We could remove the partition here, B, and then you would have the number of vertices would be 0 now if you remove the partitions, and the number of edges would just be 1. And again, if you remove all 3 of these edges, you just have the 1 remaining. It's going around here, and you don't need to stop anymore because you remove this and you just keep going. So there's just the 1 edge, and then there's just the 1 face as before. So it's just another way of looking at this, but let's stick with the way of constructing it via the fundamental polygon, this thing here, and we get this. So that's not too bad. The next two are a bit harder to see, but we'll give it our best shot. So far, the surfaces we looked at can be embedded in 3 dimensions. That would be the cylinder, the torus, and the Möbius strip. In the example we have here, the Klein bottle, it can't be embedded in 3 dimensions, and we'll discuss that a little bit more as we get through the next few slides. In terms of the oil characteristic, we need to keep in mind that there's a twist when we're doing the joining of the edges. So the rectangle is the only face. The 2 edges labeled A are glued together, and we also glue the edges labeled B, but there's a twist. So when we're done, we have 2 edges when we join we do the joinings as directed here. Then the last step, and I'll show you this in a little more detail later, all 4 vertices are glued together, and that leaves just 1 vertex. So our v minus e plus f is a 1 minus 2 plus 1, and we get 0. The Klein bottle does not intersect itself. However, the typical visual representations in the literature show the Klein bottle is intersecting itself. And we'll see that on the figure in the next slide. In fact, there's even physical glass or porcelain models that you'll see, but they're not 100% accurate. They're just kind of a shortcut representation, and I'll explain that a little bit more as we proceed. So the self-intersection can be resolved by placing the Klein bottle in 4 dimensions, where the 4th dimension is time. In this way, the apparent points of intersection exist at different points in time and thus do not intersect. So there's a construction of the Klein bottle in the Wikipedia article entitled Klein bottle, and actually I took some of the figures from that article in the next 2 slides, and I'll go through those. I also wanted to point out there's a nice animated version of the construction, and it's in the YouTube video entitled "What Does the 4D Klein Bottle Look Like?" And I'll put the link to that in the information associated with this video. So we just have the fundamental polygon here again, which we've seen that before. And this is what happens when you do the prescribed joinings. And this is the problematic point here. This intersection is not really an intersection. It's just the way we show it in 3 dimensions. But if you let time be the 4th dimension, then these points overlap, but at different points in time, and so effectively there's not an intersection there. So it's kind of a nice, pleasant shape. And as I say, there you'll see at hobby shops or museums, sometimes you'll see glass models of this, and it's not 100% accurate, but you will see these things for sale as usually in glass, maybe in porcelain in some cases. On this slide and the next, we'll go into more detail concerning the construction of the Klein bottle. We start here with the fundamental polygon. We've seen that a few times. And we'll do the first joining where the vertical edges are joined here. And just wanted to draw this in here. So what was 4 vertices are now 2. These 2 are joined. And let's continue. We're going to bend this and start getting into the shape of the Klein bottle on the next slide. So we see here we're starting to bend. We put the cylinder on its side first, then we started to bend it. Now if we continued just the way we did with the torus, then this would be going in the opposite direction of this. This is going counterclockwise, and this is going clockwise. So we can't match this up with the arrows going the same way. So this is where we punch a hole through the cylinder, and then we come up through here, and then we bend it, and then we make the join. So in terms of let's make that in blue. So we have a vertex here, vertex here, vertex here, and here, and then here, and here. So you can see that when we finally do that last joining, there's only one vertex left. It's all 4 of them coincide, and then we still have this edge and this edge going around this way. Use the pointer here. So one vertex at the end, and then one red edge, and then one blue edge, and then everything is one. This is all one face. So that gives us our Euler characteristic of 0. So let's talk about the projective plane. And I realize that what I'm showing here is in terms of the fundamental polygon doesn't look much like a plane, so a little bit of explanation is needed to convey that, but we'll do that on the next slide. In terms of the Euler characteristic, the real projective plane, which is represented as RP squared, real projective, and then 2 just means two-dimensional, has one face, 2 edges, and 2 vertices, with V1 glued to V3 and V2 glued to V4, or whatever you want to call the word. I use the word glued here, but you could say associated or mapped. So the Euler characteristic value for the real projective plane is V minus E plus F, and it's 2 vertices when we get done, minus 2 edges, and then just one face. So we get 1. So that's a new number for us. We had 0 and 2 up until now. We'll see that you can get a lot of different numbers when you start combining these, but that's in the next lesson. So the mappings are a bit hard to see when represented this way, but this representation on the bottom is equivalent. And if you just look at, let me draw a few points. So a point here, sorry, this is kind of blob, but you get the idea. It gets mapped here, and if you had, say, a point, because you're twisting it, and then say a point down here would get mapped here. So what's happening is points, if you kind of deform this into a circle, like we have on the bottom, what's happening are opposite points are getting mapped into opposite points. So it's a lot easier to see it this way here. You take any point on this circle, when you get done with the mappings, the point gets mapped to the opposite side. This point gets mapped the same. If you had a point here, it would get mapped directly across. So this is equivalent to this, and this is a bit easier to see in terms of how the points get mapped. Let's continue on the next slide. Now, what we had on the last slide is known as the projective plane, but as I say, it doesn't look very much like a plane. The normal starting point for a projective plane is, in fact, a plane like we have shown here. And the only difference is you add what's called the point at infinity, or points at infinity. So what I've shown here are a bunch of parallel lines with a given slope, and the point at infinity is where they intersect. So if you go infinitely in this direction or infinitely in the negative direction, it's the same point. It's just one point for these parallel lines, and they all intersect at that so-called point at infinity. If I rotated if I had another set of parallel lines, let's say there were, I can do a feeble attempt here, but if you had, I'll just draw 2. If you imagine they're parallel. So if we had a bunch of these parallel lines, let me do one more. Then there would be another point at infinity that if you go this way or this way, you reach that point at infinity. So for each set, which is infinite, each infinite set of parallel lines, you have a different point at infinity. And when you put all those together, the plane itself, and then all these points at infinity, one for each of the infinite number of slopes, you get what's called the projective plane. So the tricky part is showing how this is equivalent to what we had on the previous slide. And there's a nice video that does that much better than I can do, but I'll just kind of summarize things on the next slide, and I'll point you to that video, which I would strongly recommend having a look at. So let's complete the thought here in terms of the projective plane. We saw that on the previous slide that the projective plane is just the two-dimensional plane, and then for each set of parallel lines we add a point at infinity. So we can map that to something called this hemisphere model. It's something from what's called single elliptic geometry. And I described this in a section of my book that's not related to what we're talking about here in terms of surfaces. I have a section on non-Euclidean geometry, so you're welcome to have a look at that. But just to focus on the problem at hand, in this hemispherical model, the lines are semicircles, so we see A and B are two lines, and they're sort of equivalent to what we're calling parallel in the projective plane if they share these common point along the boundary here on the bottom. So A and B would be parallel, and then C is the actual point at infinity. And if we took the semicircles going, was B as its endpoints, so they would be going along this way and across the top. Excuse me, that would be another set of parallel lines. So this modified hemisphere model is equivalent to the projective plane, and that's the hard part to see, but there's a very nice video which I highly recommend. I'll put it in the information to this video, the link to it, and it's from the Open University. It must have been recorded before the internet. I think somebody saved the video and then just put it up on YouTube. You'll see when you look at it. You could tell it's an old video, but they did a really good job of actually building physical models showing how these different representations of the projective plane are the same. So have a look at that. There's also another Open University page that's much more recent, and that's a written course that's online, and I'll give you the link to that too. You might want to look at that. So just coming back to what we have here, the semicircles sharing the same endpoint are parallel lines, and they're equivalent to, or at least mapped to, the sets of parallel lines in the projective plane. And then the trick here is if you topologically, you can just squish this down flat, and then all these points on the hemisphere are interior, and then the points along the edge, which are mapped to points diagonally opposite, are these points here. So this model is equivalent to this model, and as we saw in the previous slide, this is equivalent to this. So the projective plane from the very last slide is equivalent to this is equivalent to this, and this is equivalent to this. So that's why the term projective plane is used here. Depending on what you're trying to accomplish, different models are easier to work with and visualize. And as I say, I think this particular video here will kind of help you see things a little bit better. So that's the end of this lesson, and I have a few more on this topic of surfaces, so stay tuned.